Welcome to part 2. So how well the air-fuel gasoline charge burns determines how much BMEP can be applied upon piston head during each power stroke. How well the air-fuel gasoline charge is heated up by compression determines how well and thorough the air-fuel gasoline charge will burn. Compression itself is powered by the power lost to keep the engine running, and only BMEP is directly proportional to the torque output and becomes RPM available at the engine's crankshaft, which ultimately becomes usable power available, or brake horsepower. Brake mean and effective pressure, torque, and brake horsepower are all directly proportional to each other and are all harnessed by the burning of gasoline fuel. So in other words, the compression sets the air-fuel charge up for burnability, lack of a better word. If you compress the air-fuel charge to the optimal compression, then it's going to heat the air-fuel charge up and put it into a vapor state so that the combustion is thorough and little or no unburnt gas remains. This allows for better emissions and maximizing BMEP, because the BMEP is directly powered by the burning of fuel itself. Proper compression within engine design limits determines how well the air-fuel gasoline charge will burn. Optimal compression will result in the maximum amount of combustion of the given air-fuel gasoline charge, and thus results in the most amount of thermal energy released from the gasoline, ultimately becoming pressure on the piston head to drive the power stroke, also known as BMEP. The BMEP is then exerted against piston head surface area and becomes dynamic force upon the piston and connecting rod. The connecting rod then absorbs this dynamic force during the power stroke and is attached to the crankshaft's crank pin, converting linear motion into rotational motion in the form of RPM and torque at the end of the crankshaft, ultimately becoming usable power output in the form of brake horsepower. After the power stroke ends, the rest of the power is used to push the spent air-fuel charge out through the exhaust stroke, then draw in new air-fuel gasoline charge, the intake stroke, followed by powering the compression stroke to restart the duty cycle. The rest of the power also needs to overcome engine moving parts friction, rotate the camshaft, overcome valve spring pressure, overcome camshaft lobe resistance against the hydraulic or solid lifters and roller rockers or push rods, as well as supply enough power to ingest and purge intake air-fuel gases and exhaust gases. 67% of the energy in the gasoline fuel is lost just to keep the engine running when at all engine speeds, and 33% of the energy of the gasoline is converted into usable mechanical power output at the end of the crankshaft in the form of brake horsepower. Regardless to how efficient a gasoline piston engine is designed to be, all other efficiencies such as volumetric, mechanical, and combustive efficiencies can greatly be improved, but the brake thermal efficiency will always remain no greater than 33% brake thermal efficiency when at no load conditions with the engine running and the transmission not engaged. This is pertinent to a 4-stroke gasoline piston engine only. Diesel heat of air compression piston engines operate at a higher percent brake thermal efficiency of around 38% to as high as 48% under no load conditions, due to the heat of air compression auto ignition setup and the fact that the air to fuel ratios in diesel piston engines are very complex and fluctuate greatly between 15:1 to as high as 101 AFR. This is primarily due to highly complex electronic fuel metering systems and fuel rail pressures which exceed 120,000 psi, making more stable and accurate fuel delivery charges during each power stroke. But in regards to gasoline piston engines, compression is designed to act as an air-fuel heater to allow the air-fuel gasoline charge to homogenize into a vapor state due to compression heating high enough to reach a vapor state, but low enough to prevent auto ignition and subsequent detonation, knock, or dieseling. Compression will cost power out of the fuel to sustain and could only be considered an increase in power based on the contributions compression makes in heating the air-fuel gasoline charge, allowing for as complete and thorough combustion as possible. Only when a thorough and complete combustion of the air-fuel charge occurs will BMEP potential increase, and with the optimal compression, not too low and not too high, the maximum air-fuel gasoline charge heating will occur, allowing for a thorough and complete combustion of the air-fuel gasoline charge. Not only will optimal compression allow for a thorough or near complete combustion of the air-fuel gasoline charge, also unburnt gasoline emissions, HO, will be reduced or even eliminated, only leaving carbon monoxide, CO, and its conversion into carbon dioxide, CO2, by the catalytic converter, and then, of course, oxides of sulfur, SOx, and oxides of nitrogen, NOx, remaining to exit the exhaust manifold. With gasoline fully vaporized from its liquid state due to optimal compression prior to the spark ignition event, this also reduces or eliminates the amount of unburnt gasoline which will carbonize through the engine's internal flow systems and contaminate the oil through the positive crank ventilation PVC system, an acceptable blow-by that escapes past the piston rings during each power stroke into the oil in the crankcase. This results in longer run times before oil changes are required. Right now in 2017, the typical 2017 automobile has a compression ratio of 11.3 to 1 and an oil change runtime of over 6,000 miles, compared to second generation automobiles which operate around 8.5 to 1 compression ratio and require oil changes every 3,000 miles. The gasoline is essentially reaching a pure vapor state by the time the ignition event occurs due to the higher compressions. It is important to know that gasoline must have enough inertia in its liquid form upon delivery into the ignition system to effectively reach the cylinders and not reach a lean condition. Many people have suggested vaporizing gasoline into the likes of propane gas at room temperature so that a pure gas is ingested into the cylinder based on the fact that 1 liquid U.S. gallon of gasoline will vaporize into 160 dry U.S. gallons of gasoline vapor to increase percent brake thermal efficiency, but only the cold vaporization at lean state may effectively vaporize, resulting in over-vaporization after the engine reaches a higher operating temperature, resulting in hot spots and lean conditions. Gasoline vaporization is best induced on the compression cycle and never any time before, because as the engine heats up, cold vaporization will work initially, but over-vaporization will occur as normal engine temperatures are reached. Automobile manufacturers have done very well to cause maximum vaporization of the gasoline fuel, as well as keeping an electronic fuel injection system which digitally calibrates and meters the gasoline AFR, or air-to-fuel ratio induction, to 14.7 to 1 as fast as possible. Combine this with a variable valve cam timing technology calibrating piston-induced airflow by regulating cam actuation, keeping the pressure and velocity balance at a constant at all engine speeds so that the piston doesn't slip the air induction. This results in above 100% volumetric efficiencies without the need for a turbocharger. All in all, most if not all of the gasoline is burning, but remember, in a lower compression piston engine that's gasoline and 4-stroke, more volatile fuel, gasoline, is powering the engine, and the maximum percent brake thermal efficiency will peak at no greater than 33%. The rest of the energy stored in the gasoline is lost to keep the engine running. So gasoline has 20,000 BTU per pound regardless of octane. Gasoline has a fuel density of 6 pounds per 1 US gallon. If 1 BTU per second of heat energy is released, that will equal 1,056 watts and 1 horsepower of 746 watts. So 67% of 1 BTU per second heat output in the form of burning gasoline will be lost just to keep the engine running. Whatever power that remains will become available mechanical power at the engine's crankshaft in the form of brake horsepower. Octane slows down the flame front speed of gasoline during higher compression and is no longer an issue with late model automobiles manufactured after 2010 due to the advancement of anti-knock sensor governed EGR valves. Using unleaded regular gasoline 87 octane in automobiles manufactured after 2010 with 11.3 to 1 compression ratio, which have anti-knock sensor governor EGR valves, will not cause detonation or knock, and is no longer an issue. All gasoline octane grades 87, 89, and 93 contain phosphate detergents and clean fuel injectors and fuel lines by default. Using octane grades above 87 on late model automobiles made after 2010 or 2011 is really a waste of money. Only on cars made prior to 2008 to 2005 with compression ratios higher than 9 to 1 should 89 octane be used, and higher than 9.8 to 1, 93 octane should be used to prevent detonation or knock of the air-fuel gasoline charge. But all cutting-edge automobile manufacturers, whether U.S., European, Japanese, or South Korean, made after 2011, will have anti-knock governed EGR valves, and octane grade is no longer an issue and operate perfectly on 86 and 87 octane. So we know the U.S. car makes. European is like Volvo and BMW and Mercedes. And of course there's British, they make the Land Rover and the Jaguar. And then Japanese, we know there's like Nissan, Toyota, Honda, and South Korean is Hyundai. So these are all the cutting edge leading automobile manufacturers. The purpose of this lecture is to introduce the basic understanding of compression in a gasoline piston engine as a form of an air-fuel heater to allow the air-fuel gasoline charge to reach an optimal vapor state, allowing for as complete and thorough combustion as possible with as little or no unburnt gasoline remaining. When this happens, then the brake mean effective pressure maximum potential at given engine RPM will be reached. And remember that compression is part of the power loss to keep the engine running. Thanks for watching this video. Like and subscribe, and have a great day.